Yeah, so this is the generative AI tutorial. Thank you all for coming. If you were at the tutorial last week, this is going to cover the same material. So you might find it a little bit boring, but if you haven't attended before, we're going to spend the first hour or so just talking about language models and how they work. And then we're going to spend the next hour and a half, 2 hours, on a practical exercise where I and the various TAs will be around to help you figure out how to actually use language models. All right, so before I get started, though, I'm going to turn it over to Carolyn to talk about this really cool hackathon series that's happening this summer.
So this tutorial is part of a whole series of events that we're having all summer. I'm sure that you guys already know because you were at our website to register. Some of the exciting things that we have going on are 3 hackathon series. The Education and Future of Work hackathon is already in progress. We had 58 people sign up. We had our first event yesterday where people came and gave project pitches and started to form teams. And in 2 weeks, those teams will present their team proposal, and 5 teams will be selected for the hackathon weekend, at the end of which one team will be selected for a cash prize. And the goal of the cash prize is to support the development of the hackathon project into a real end user application. And that's funded through our Heinz School of Public Policy. So we're no longer taking registrations for Education and the Future of Work, but the other 2 are still open: Medicine and Public Health and Finance and Economics. And so we encourage you guys to go ahead and sign up. And I will be pasting these links into the chat so you can go ahead and register if you're interested. We had a really great time yesterday. People from all over the world were making their pitches, and it was really exciting to see 12 different themes emerge from the ideas, covering the gamut of applications within the area of education and future of work. And I'm really excited to see what will come out of the other 2. The equivalent of that session will happen next weekend for medicine and public health. So at the end of all of our events, we always ask people to go ahead and give us their feedback. And also on that form, people can ask to join our Slack. But Daphne has already given you guys a way to directly sign up for our Slack. But if you want to give feedback on the series or just suggest some ideas for how to move forward with this effort, we're open to your comments at bit.ly/GenAI Reflect. And I have mentioned several times our certificate in computational data science getting off the ground in the fall. And now we have an official website where you can get much more information on what that will entail. And so I will also paste that link into the chat. And now I'll be happy to hand this back over to our fearless leader.
All right, thanks, Carolyn. That all sounds pretty exciting. I'm glad that the pitches went well yesterday. So what are we going to be covering in today's talk? So I saw a lot of you filled out the Google form that asked you what you're interested in covering. So this is largely based on what people said that they were interested in. First, we're going to talk about just what is a language model. Then we're going to go over all of the building blocks of creating a language model. And next, we're going to talk about decoding strategies. So how you actually use a language model to do generation. We're going to briefly talk about language model architectures and what led to the development of the transformer, which is what people almost always use today for large language models. And finally, we're going to talk about the importance of training and fine-tuning data. So you might have noticed in the abstract, we originally said we were going to talk about image diffusion models, but then I realized I had 120 slides already. And so this won't be in this tutorial, but maybe I'll try to fit it in a future one. All right, so what is a language model? An important point to make is that language models aren't actually generative. Instead, we'll be talking a lot about likelihoods. So there's the conditional likelihood of a word given the previous words in a sequence, and there's also sequence likelihood, so a likelihood of an entire text sequence. So a language model is just any model that outputs a probability distribution over the next token in a sequence, given the previous tokens in that sequence. And you can see the math through that here. And historically, language models were n-gram models, so statistical n-gram models. And this meant that they just counted the number of times that a word followed some other set of words in some corpus of training data, and then they predicted a probability based on that. So as a practical example, suppose we just have some large corpus of text C, and we note that the word apple follows the words eat the, 2% of the times eat the occur in the corpus. This just means we'd say that the probability of apple given eat the is 0.02. And since eat the apple is 3 words long, we'd call this a 3-gram model. So let me go back a slide. One of the issues you might note here is that you can't really model things that aren't in the training set. So if the words eat the apple in that sequence never occurred in your corpus, you would give them a probability of 0. And so you don't ever assign probability to things that you've never seen before. And also it's computationally impractical to set your n-gram size to things that are really large. And so back when people were doing these statistical n-gram models, you might use n-grams of like 4 words long, 5 words long at max, but you wouldn't look at a context of hundreds of words or thousands of words in order to make your prediction. Someone asked in the chat about getting a recording of today's lecture. Yeah, once all of the tutorials are over, one of the recordings of the tutorials will be put online. Okay, also feel free to interrupt me with questions. I should have said that. You can either put questions on the chat, which I may or may not see, or you can just turn on your mics and ask questions. So any questions so far?
I'll just mention that if you do ask a question with your video or audio on, then that video and audio will be included in the recording. So you would be agreeing to have your that recorded aspect sort of shared when the video is made public. So just so that you know, the chat will not be made public.
So a few questions. What is an n-gram model? So an n-gram model is just what we're showing on this slide here. So you have some text corpus and you're just counting for every 3 grams. So 3 gram is just a sequence of 3 tokens or words. How many times does word 3 follow words 1 and 2 in your training corpus? And then you have a probability of word 3 given words 1 and 2 that you're just computing from your corpus. So that's an n-gram model. Someone asked if I will be covering ethics, and I will not be covering ethics in this talk, although I think there's other talks in this series that have touched upon ethics or will touch upon ethics. And it's just the number of words or tokens. So for now, I'm going to use the words word and token interchangeably, but we'll come back to that. So as you can see, we've been talking.
I had a question.
Yeah, of course.
So sorry to cut you off, but other than the computational efficiency, if the value of n is too large, is there any other downside of using an n-gram model?
So yeah, there's two big issues. One is you can't set your n to be too large because then you just get a model size that balloons out. The other issue is that it's really challenging with statistical n-gram models to represent text that you've never seen before. So in this talk, even though I already gave this talk a week ago, I am most definitely saying sentences I have never said before in my life. These are new sentences. So humans don't just regurgitate things that have already been said before. We say things that are new. And a new n-gram that has never been said before won't be in the training corpus, and so it'll have a probability of 0.
Thank you, ma'am.
So this is an important point I already said, but language models are not inherently generative. We're going to be talking about likelihoods. And so I mentioned on the very first slide, computing a sequence likelihood. And so we know now that language models output the likelihood of the next word given the previous words. And we want to be able to compute the likelihood of an entire sequence. Well, how can we do this from what language models output? And we can just actually break down the sequence of likelihood using the chain rule. So the probability of the sequence I eat the apple is just the probability of apple given I eat the times the probability of the given I eat times the probability of eat given I times the probability of I. That's just the chain rule. And so this is how we can compute sequence likelihoods. Oops, sorry. So one other piece of information that's useful to know is that language models can either be designed to just predict the next word given the previous ones, or they can be designed to predict the next word given the previous ones in that sequence and some additional conditioning sequence. And so on the left, I'm showing like what an unconditioned language model looks like. So you just have the probability of a word given the previous words. And examples of systems that use this sort of technique are GPT-2 and GPT-3 and Llama. And on the right, I'm showing what a conditioned language model looks like. These are sometimes called sequence-to-sequence models, especially in like older, like 2018, 2017 literature. You'll see sequence-to-sequence models talked about a lot. And then some examples of encoder-decoder models, these conditioned models on the right, are T5, which is a very popular open source model from Google, and most machine translation models. Because in machine translation, you want to be converting from, let's say, an English sentence to the French sentence. And so you need to condition on this additional English sentence. And I'll be giving examples of both unconditioned and conditioned models in this talk, but most of what I say for one translates directly to the other. Yeah, GPT-4 is an unconditioned model, so it doesn't have this extra sequence. So I would say that most modern models that are just designed to like in a monolingual way, so designed to just take text in one language and not like do any like specific task, tend to be unconditioned, but don't have that extra conditioning sequence. So most of the state-of-the-art models you would use would be on the left here. Someone asked about BERT. BERT is actually a different paradigm, which I didn't put here. So BERT actually doesn't generate the probability of a next token given the previous tokens in the sequence. It uses this masked objective. So given that you've hidden some of the tokens in the sequence, you replaced them with like this mask that you're hiding them, can you predict what's behind the mask? So it doesn't really fall into either of these paradigms. All right, so we're going to move on and talk about the building blocks of language models. So in these pictures here, I'm showing what the neural network kind of looks like. So you can think of these trapezoids I've listed as encoder and decoder as neural networks. There's some neural network in there. And so if you're doing an unconditioned language model, you have just a decoder and we call this a decoder because it decodes a probability for the next token in the sequence given the previous tokens. And in conditioned language models, we have an encoder, which is a neural network that takes, let's say we're doing machine translation, it'll take your English sentence that you want to translate, encodes it into some hidden state that represents that English sentence. And then you have your decoder, which takes as input that hidden state and the tokens of the target sequence that you're trying to predict. Let's say we're trying to convert from English to French. Those will be like the French tokens. And then it predicts a probability distribution for the next token in that French sequence. And so going back to the question about BERT, BERT actually is an encoder-only model. It doesn't have a decoder. It doesn't have this thing that outputs the probability of the next word given the previous words. So if I had BERT on this figure, it would only have the encoder component. Any questions so far? All right, so I've sort of stressed this conditions versus unconditioned split, but honestly, it doesn't matter that much anymore. And like, I think people thought it mattered more in the past than it does today, because theoretically, any task designs for a decoder-only architecture can be turned into one for an encoder-decoder architecture and vice versa. So for example, if your task is just continuing a sequence, you can have a model that predicts the probability of this entire sequence. Or you can have a model that predicts the probability of the suffix of the sequence given the previous sequence, given the prefix to the sequence. So these are sort of interchangeable, although you can see that for this task, using a decoder-only model sort of makes more sense because it's unclear what should be a prefix and what should be a suffix. And if we look at machine translation, which is sort of the classic example of a conditioned model, you could say, I have this sequence that has English : the hippo ate my homework, French : l'hippopotame a mangé mes devoirs. So I have a terrible French accent. And so you could just compute the probability over that entire sequence, or you could turn it into an encoder-decoder condition system where you have the probability of the French sentence given the English sentence. And so you can see for machine translation, it kind of makes more sense to have this conditions encoder-decoder model, but you can frame it as a decoder-only version. Any questions? Okay, just to summarize the terms that I've talked about so far. So we have an input sequence, which I'm going throughout this lecture to refer to using the variable x sub 1, x sub t. You have a target sequence, which I'll refer to as y sub 1 to y sub t. And you have an encoder that takes the input sequence, a decoder that takes some representation of the input sequence and the target sequence, and then makes a prediction for the next token in the target sequence. So something I've glossed over so far is what actually are these x sub y and y sub y. So I've been using the words token and word kind of interchangeably, but ultimately we need a system that takes text and turns it into a sequence of discrete tokens. And this is called tokenization. So tokenization is just the task of taking text or code or music or whatever you want to represent and turning it into the sequence of discrete items, which we'll call tokens. And so vocabulary is a list of all of the tokens that are available to use. And so I've been using the word and token kind of interchangeably because back in the day, one of the most common tokenization strategies was to split text into words. And so that's what you see on the last row here. So I could just say every word is a token. On the opposite extreme, and this is the absolute simplest thing you could do because you don't need any fancy parsing, is you could use character level tokenization and just say every character is a token. So that's what's being shown in the top row here. But in practice, what people actually do is something in between this. They do something called subword tokenization, which I'm showing in the middle row here. And subword tokenization for common words, which occur commonly in the training set, like my and homework, these end up being tokens. But rare words like hippopotamus get broken up into multiple tokens. And the reason why this is valuable to do is your vocabulary needs to be finite. So you need to say, I have a budget for 50,000 tokens in my vocabulary, 100,000 tokens. And obviously there's more words in English or in any language than 50,000. And so what happens when you are using the word level tokenization is if a word occurred that wasn't in the 50,000 most common words in English, you would just replace it with an unknown token, of a token saying, I don't know this word, because you had no way to represent it because it wasn't in your top 50,000 words that you would put in your vocabulary. And subword level tokenization gets around this by when you have these rare words, they can be broken up into their constituent pieces, and that can be represented. And so every state-of-the-art model you'll see is uses some version of the subword level tokenization. Someone asked, what do the hashtags mean in this case? So the hashtag means that this is a continuation of the previous word. So you can see that they only occur on the continuation of the word hippopotamus. So it's basically saying, don't put a space between this token and the previous token. Someone asked, since a seek-to-seek task can be framed as an unconditional task, is the decoder only better than the encoder-decoder model? It seems to provide more flexibility. Yeah, so one reason why people did encoder-decoder models is so that you could have a representation of the entire sequence in the encoder. And so you have some sort of like fixed representation of that sequence that you're conditioning on when you're doing generation for the target sequence for what you want to actually generate. And it used to be like wisdom that this was like crucial, it was necessary to do this. But increasingly, people are realizing that you can get away with not doing this, of not having that separate encoding step, and do just as well on many tasks. So I think that we as a field are moving away from encoder-decoder models. Although one nice thing about encoder-decoder models is because you're encoding that input sequence, you have a representation of that input sequence. You have a set of vectors that represent it. And if you want to do like various types of analysis, it's sometimes nice to have those embeddings so that those can allow you to do other tasks, which might be harder to do if you just had a decoder only model. So someone asked, are you saying that decoder only models can produce novel things afterwards? I thought you said earlier this is not possible. So when I was talking about statistical language models will not give probability to novel sequences. Statistical language models don't have any fancy neural networks in them, so they're not learning any patterns about the data, which can be used to extrapolate to novel sequences. But if I go back to this figure, sorry, one sec, wrong direction. So both the encoder and the decoder here are neural networks. Let me go back to this figure. So these are the decoder, the encoder, and the decoder here are all neural networks. And so because you're using neural networks here, you have the ability with either a decoder only model or an encoder-decoder model to represent novel sequences. And so the thing that allows you to do generation, we're going to get to generation later, is the fact that this decoder outputs a probability distribution over what the next word in the sequence should be given the previous words in the sequence. And this decoder is present in both the unconditioned language model and in the conditioned language model here. Someone asked, does encoder-decoder offer less error since it seems to work in a more structured and limited way? Yeah, so I think people found, especially for tasks like machine translation, where it's very clear that there's like this split between sequences, I think it has been found that it works better to have these separate steps. I don't know what is state of the art on many other tasks right now, but that's something that we could talk about. If you ask a question on Slack, we can talk about later. Okay, I'm going to move on. All right, so we talked about turning text into a sequence of discrete tokens. But one of the fundamental limitations of neural networks is that they don't operate on discrete things. You can't train a neural network on discrete things because optimization on discrete space is very difficult. So instead, we need to have some sort of continuous representation, so a vector in continuous space that corresponds to each word. So suppose we've decided all of the 50,000 words in our vocabulary. That's what I'm showing on the left here. And now we have a vector representation that we want to associate with each of these words. And when we first start training our language model, these will just be randomly initialized, so they'll be meaningless. But as the language model trains, eventually these vectors will encode some sort of meaning for the different words. And so you'll hear me talking about the vocabulary, which is this list of 50,000 tokens, let's say. And you'll also hear me talking about the embedding matrix. So the embedding matrix gives you just the embedding for each of the words in your vocabulary. So it's a matrix that has an embedding dimension, which is often like something like 512 dimensions. And it has one row per word in your vocab. Any questions? Okay, so let's look at what the input to the encoder actually is. So you have your sequence of words or token. I'm going to use word and token kind of interchangeably, but you know what I mean now from the previous slide. So you have your sequence of words. You map them to indices, so the token index. This is the index into the vocabulary. And then for each of these, you can find their embedding by looking in the embedding matrix. And so the input to the encoder is actually just the sequence of embeddings from the embedding matrix. Someone asked, is the embedding learned or mapped? Very commonly, it is learned in the sense that you randomly initialize your embedding. So at step 0 of training, these will just be random vectors of some sort. And then as you train, they'll eventually have more meaningful representations. So let's look at what the encoder outputs. So I've already kind of talked about this, but the encoder outputs just a sequence of hidden states, one per position in your input sequence. And I'm going to refer to these as the hidden states of the encoder. And these will be purple, pretty purple rectangles in all of my slides. And so now let's look at both the encoder and decoder together. So this is the same picture on the left of the encoder. Now we can see what the decoder takes as input. So the decoder takes as input the embeddings of all of the hidden states from the encoder, so the encoder's outputs, and it takes the embeddings of the vocab from the embedding matrix of the words in the target sequence. And so when it predicts an embedding that I'm going to call y hat sub t, which we really want this orange rectangle, this embedding that's getting predicted, to be as close as possible to the embedding for the true next token in the sequence. So what we're trying to optimize for in a language model is making this predicted embedding look as close as possible to the embedding for the true next word in the sequence. Does that make sense? And we'll talk about how we do that in a minute. So remember that we are training neural networks on training data. So we have training data. In this case, I'm showing a machine translation example. So we have pairs of English and French sentences. And so the next word in the French sentence, I didn't show this, but the true next word in the French sentence is the word ah, because that's the past tense that you need for saying the hippopotamus ate my homework. And so the true next word is ah. We can look up what the embedding for ah is in the embedding matrix. And we want the embedding for the word ah in the embedding matrix. We want this predicted embedding y hat sub t to look as close as possible to the embedding of the word ah, because that's the actual next word in the French sentence. And so that's how we train these models. Does that make sense? Yeah, so I'm going to be using y hat sub t to refer to the prediction. Often we put a hat on top of a variable to show that it's a prediction. So y hat sub t is the prediction of the model, and y sub t would be the true next word in the sequence. Is the embedding changed during training? So as we're training, so these encoder and decoder, they have a bunch of weights in them. They have a bunch of parameters that are getting learned. And so at every step of training, we modify all of these weights within the model, within these encoder and decoder, so that we make this y hat sub t look just a little bit closer to y sub t. So at every step of training, we're modifying the weights in order to try to get this predicted y hat sub t to look a little bit closer to the true one. Any questions about that? So as I mentioned, ideally we want y hat sub t to be as close as possible to embedding of the true next token. And the question becomes, how do we actually check for that? So we have our embedding matrix E that we've already talked about. We have this predicted embedding y hat sub t. And we can just do a matrix multiplication because the dimension of the prediction y hat sub t is the same as the embedding dimension of our embedding matrix. And when we do this matrix multiplication, we get a vector back, which we call the Logits vector. And the dimension of this Logits vector is the vocab size. So now we have one real valued number for each item in our vocab. And these Logits are scores. They just tell us how confident the model is that this word could be the next word in the sequence. So you can think of it as we have all of our embeddings for every of the word in the vocabulary. And for each of the words in the vocabulary, we're taking the dot product between the embedding for that word and the y hat sub t, the embedding predicted by our decoder. And when the dot product is high, there's going to be a large score in the Logits for that position. And when the dot product is low, there's going to be a small score in the Logits for that position. So someone wrote, it sounds like training is basically trying to get it to be right based on some set of problems we have prepared along with the right answers for each of those problems. Yeah, so that's exactly it. So when we're training, ultimately we just have a sequence of text, and we want to make the language model really good at modeling that sequence of text. So we wanted to make it really good at putting a lot of confidence, at putting a high score on whatever the true next word is given the previous words, and a low score on all of the other words. And that's what we're going to be optimizing for. So just as an example, so this position here in the Logits might be the score for dog. This one over here on the right might be the score for apple, and so on. All right, any questions about this before we move on? Okay, can you explain the shape of E and Y hat again? Yeah, so the embedding matrix has the dimensions, the vocab size, so the number of words in your vocabulary, times some embedding dimension. Very commonly, this embedding dimension will be 512. So if you have 50,000 words in your vocabulary, this embedding matrix will have the shape 50,000 by 512. And then y hat sub t, the prediction from the model, will be a vector that just has the dimension 512. You are saying the embedding matrix at the beginning could be random, so the training going to train both the embedding matrix and the weights. Yes, this is correct, sir. So Peng asked, are you training both the embedding matrix and the weights of the neural network at the same time? And most commonly, that is what is done. I would say like 4 or 5 years ago, people were doing things like initializing the embedding matrix of some sort of already learned representations of the words. And that's fallen out of fashion. People don't really do that anymore. For the most part, we just randomly initialize the embedding matrix and we learn the embedding matrix at the same time as we're learning the weights within the decoder and the encoder. Someone asked, why is the score of dog and apple there? So what I'm just trying to show here is that you have one item in the Logits for every word in your vocabulary. And so at some point, I'm assuming that the word dog is in your vocabulary and the word apple is in your vocabulary. And so I just put these arrows here, but I don't know where they could actually be. So I was just me trying to make it clear that you just have one score for each item in your vocabulary. Okay, any other questions or ones I missed on chat? Feel free to speak up too. How does the embedding matrix relate to a co-occurrence matrix? So in the embedding matrix typically is learned. So a co-occurrence matrix is something that you can compute that's basically saying how often do all of the words in your vocabulary co-occur with somewhere? How often does the word apple co-occur with the word dog? How often does the word believe co-occur with the word dog? And you would create a vector for the word dog that basically has positions for each other word in the vocab size saying how often they co-occur. This is not how the embedding matrix works because it's all just learned. And it has some dimension that's usually much smaller than the vocab size. So it'll usually have like 512 or 300 is a common embedding dimension size. Yeah, someone else put in chat, co-occurrence matrices are also very sparse. That's a true statement because most words do not co-occur with the word dog. And so if you were using a co-occurrence vector for dog, you would have a lot of zeros in it. Someone asked, is there a specific meaning interpretation if the Logit score of a given word is high? And that leads very well to my next slide. So I'm going to go on. So the answer to that is no. These Logits are unnormalized. They can be positive or they can be negative, and there's no meaning to them. But we as humans like there to be meaning to things. In particular, we would love if we could talk about probabilities. So rather than saying the score in the Logits vector for the word dog is large, we would like to be able to say the probability of the word dog is 0.1. And so how you go from these unnormalized Logits into probabilities is to use the Softmax function, which is what I'm showing here. And so as a concrete example, suppose we are trying to predict the 5th word in the sequence the dog chased ba, and we want to know the probability that the next word is cat. Well, we could say that the probability that the next word is cat, given the sequence the dog chased ba, is equal to the e to the score in the Logit for cat. So we look in that Logits vector for the position corresponding to cat, to that score. And then we just divide this by a normalization term so that everything sums nicely to 1. And then we might get that the probability of cat is 32%. And so this is how we get actual like meaningful interpretable numbers from the Logits that aren't just these unnormalized scores. Any questions about this? Okay, so you might ask, why the Softmax? Why does this make sense to use the Softmax function? And we actually see why it makes sense when we look at the loss function used to train these models. So right now I'm showing the loss function that we use to train language models. And you'll often hear this referred to as negative log likelihood. You can see the negative comes from the fact that there's a negative, and log becomes from the fact that there is a log, and likelihood is just the probability of the next word in the sequence given the previous words. And you do this at every position in the sequence. So that's why you have this summation from t equals 1 to the length of the sequence. And so just to reiterate, the portion of the equation I've highlighted here is just the probability the language model assigns to the true T word in the target sequence, given the input sequence X and the previous tokens in the target sequence. And I'm using I star here to refer to the index into the vocabulary of the true T word in the target sequence. So if the true T word in the sequence is the word dog, then this would be the index into the vocabulary of the word dog. And so our goal is that the language model's prediction is as close as possible to the true next word in the sequence. So we already talked about the fact that we get this probability distribution by taking the softmax. So I've just plugged in the softmax equation from the previous slide, and you can see that here. And this E times Y hat sub T is exactly what I showed you before. So this is just the Logits vector. And what we're doing is we have this Logits vector, and we don't care about any part of it except for the position that is the true next token in the sequence. So what we care about is the position in this Logits vector that is I star. So for example, we might look at the score for the word at index I star, and that's what we would get here. Any questions so far? Okay. And so you might notice that there are some nice things that cancel out or don't matter. So the log and the X cancel out, so we can just remove those. And because we're doing an optimization, we can actually just discard the denominator here, because the denominator is going to be the same for all sequences and for all positions. And so it doesn't actually matter for optimizing. And so we actually get this really nice loss function that's very easy to compute on GPUs, because it's just basically a matrix multiplication. And so this is how we actually train language models. So language models are not trained for any particular clever things. They're just trained for this objective of predicting the next word given the previous words. The way that we make this loss operate in a more clever way, and you'll see this in a lot of papers, is manipulating what the training data looks like. So everybody trains with this log likelihood loss I'm showing here. But what often distinguishes one method from another, or one paper from another, is how people design these sequences that they pass in, the sequence X and the sequence Y. I don't know how to answer that. I don't know what you're asking for an example for, Sing. But feel free to turn on your mic and talk as well. Oh, like as an example of someone manipulating the sequence, for example, if you want to do instruction tuning, like oftentimes you'll see a language model that's just been trained on all of the text in the internet, and then it's fine-tuned on either dialogue data or instruction tuning. So this is like on data to make it follow instructions. In this case, there's still the fine-tuning where they're making the model work better is still using this fundamental loss, but they're creating training data that tells the model how to follow instructions or how to talk like a chatbot. And all of that training data are still just sequences of tokens that are and we're still training of this loss, but they're creating training data that causes the model to behave in a way that's more aligned with how people want to use it. And we'll talk about that a lot more near the end of this talk. Okay, so far we haven't actually talked about generation. We've just talked about language models outputting as probabilities, but obviously you're all here because you care about generation and language models generating text. And so to actually do generation, we need something called a sampling algorithm. And this is what I have put in this thing here. And the sampling algorithm, all it does is it says, given this probability distribution predicted by the model, how do I pick a word to generate? I want to pick what the next word in my generation should be, given these probabilities that were returned by the model. And you'll sometimes hear this referred to as a decoding method or as a decoding strategy. So I'll sort of use those three words interchangeably, but they all are sort of referring to the same thing, which is this step where you're actually choosing what word to get generated. Someone asked, how much fine-tuning influencing the output probabilities? So it really depends on how much you fine-tune and on what your learning rate is. So you could have a really, really tiny data set of like 100 examples, and you fine-tune on only 100 examples. And if you do that, you're probably not going to change the probabilities too much, because you have to be really careful not to overfit on that really small fine-tuning data set. But you could have a fine-tuning data set with 500,000 examples in it, in which case you can fine-tune for quite a bit and change the weights of the model quite a bit without causing it to overfit on that data. So I think that's the big limiting factor in how much fine-tuning changes the model, is whether or not you have enough data to fine-tune on, but you're not going to cause the model to just overfit to that data. All right, any other questions? All right, without further ado, let's talk about decoding strategies. So the fundamental question we're trying to answer is, how do we sample from this distribution? And right now I've dropped the X, so I'm just talking about a decoder only model, but everything I'm talking about is exactly the same, whether or not you have that extra sequence that you're being conditioning on or not. Okay, so the absolute simplest thing that you can do is just pick the most likely token. When we call this Argmax sampling, because you're just taking the Argmax of the distribution, picking the most likely token. And I have an example here on the right. Feel free to enter your answer into the chat. If we have a language model that just has 4 words in the vocabulary and it predicts these probabilities for each of these words coming after the sequence apple, apple, if we sampled of Argmax, what word would get selected? Feel free to take a moment and put your answer in the chat. Okay, yeah, so to those of you who answered banana, that's correct. So all you need to do Argmax sampling is you look at the probabilities given to each word. You see that banana is the most likely, with 65% chance that the model thinks that there's a 65% chance that banana is the next word in the sequence, and so we would predict the word banana. Okay, so one of the limitations with doing Argmax sampling is there's no randomness. You can only ever generate one sequence because you're just always deterministically taking the most likely word. This also leads to text which tends to like be very repetitive and loopy because it doesn't ever take like risks and do something weird. And so in practice, we almost always use random sampling. And in random sampling, we're just randomly sampling from the distribution outputted by the model. So if the model says that it puts 0.65 probability on the word banana, we'd have a 65% chance of picking the word banana as our next word. So I've basically answered this question for you already, but feel free to put your answer into the chat. Yeah, so I mean, I already said it, but the answer is basically 65%. There's a 65% chance you'll pick the word banana. So it's fairly straightforward. But there's actually a problem with doing this full random sampling, which is that most tokens in the vocabulary get assigned very low probabilities, but cumulatively, choosing any one of these low probability tokens becomes pretty likely. And on the right, I've plotted a typical probability distribution outputted by a language model. So you can see on this plot, on the x-axis, I've just sorted all of the words in the vocabulary by likelihood. And on the y-axis, I'm plotting just the likelihood the model assigns to this word. And you can see that the chance of picking any one of these low probability words is really low. But there's actually a 29% chance we'll pick one of the words that has probability less than 0.01. And so even though the probability of the word web or the word monkey following I set my cat down on but is really low. So choosing the word web is you have a very small chance of choosing that word. cumulatively, there's a pretty reasonable chance you're going to pick one of these low probability words. And this actually can result in text that's just too random. And the generated text might end up incoherent, or it'll have like weird semantic errors that a human would never make. And so for this reason, we tend to, instead of just doing random sampling from the actual distribution model, returned by the model, we tend to use strategies that first modify this distribution to reduce its randomness before we do the sampling. And we're going to go over a few different ways people have modified this distribution. Any questions? Okay, so one of the relatively easy things you can do is random sampling of temperature. And so this comes from work that's much older than language models on temperature annealing. And so I'm showing the Softmax function here we use to get the probabilities, except I've added this extra term in it, this value t, which is a hyperparameter that you can set. And dividing by this t allows you to basically just redistribute the probability mass. And so if you set t to values greater than 1, as t gets bigger, you turn your distribution to something that looks more and more like the uniform distribution. And as you set t to values closer to 0, you get a distribution that looks more and more like just taking the Argmax, like putting all of the probability mass on the most likely token. And you can see that here. So you can see on the left, temperature 0.5, on the right, temperature 1.5. And in the middle, it's just the original one I showed you. So this is just the probabilities that are returned by the model of no modifications. And you can see that on the left, we get a peakier distribution. On the right, we get something that looks more like the uniform distribution. So in practice, in language modeling, in generation of language models, we almost never set temperature to values greater than 1. We almost always want to reduce the entropy distribution. Where's the temperature coming from? So this is just a variable that you set. So suppose you're working with the OpenAI API, you can just set the temperature to whatever you want. And what you're saying is, if I want to generate text that's less random, I'm going to pick a temperature that's like closer to 0. I might pick a temperature of 0.4, because that's shifting more and more of the probability mass away from the low likelihood words into words that are already high likelihood. And if you, for some reason, wanted text that looks even more random than what the language model would do by default, you could set t to something greater than 1, which would cause the distribution to look closer to the uniform distribution. Yeah, that's correct, what you put in chat. Okay, so here is another question. I'll try not to answer it ahead of time for you guys. Feel free to put your answer in the chat. Yeah, so the correct answer is indeed 25%. Obviously, you can't actually set t equal to infinity because you can't divide by infinity. But if you set t equal to some really, really big number, you're going to get something that looks basically like the uniform distribution, which means that you'll end up with a 25% chance of picking the word banana. And what if we set t equal to something that's really, how did we get 25%? So we got 25% because there are 4 words in the vocabulary. And as you set t to something really, really big, you're basically turning your distribution into the uniform distribution, which means that every one of the 4 words would have a probability equal to 25%. So what happens if we set t equal to something really, really small? Obviously, we can't do t equals 0 because then we'd be dividing by 0. So yep, the answer is 100% because we are basically turning this back into taking the Argmax. All right, so let's move on to option 4. So instead of random sampling of temperature, an even simpler approach would be to just say, I will never pick a token that is low likelihood. So while temperature sampling makes it less likely we will pick a word from the long tail, top K sampling just makes it impossible. For example, if we were to pick a cutoff of k equals 50, which I've shown in this red section I've highlighted in the plot on the right, any of these words that falls into the red section I've highlighted would never get picked. So we would set the probability of all of these words to 0, and then we would just renormalize the distribution and sample from it. And empirically, people have found that top K sampling results in higher quality generations than sampling of temperature. Okay, so option 5, which I will mention just really briefly, is an improvement on top K random sampling, and this is the one that you'll be playing around with in the tutorial. So instead of picking a K and saying, I'm going to truncate the distributions of a K most likely words at every step, instead we pick a P, which is the percentage of the probability mass we want to keep at every step. And so this means that we now have a K sub T at each step of generation. We choose to sample from the K sub T tokens, which form P% of the probability mass. And this approach is often called Nucleus sampling. And one of the advantages of it is, suppose you are near the end of a sentence, and it's very obvious that the next token in the sequence is going to be a period, because it's just very obvious this is the end of the sentence. Then maybe like 80% of the probability mass is in the word period. And so it doesn't make sense to be choosing from the 50 most likely words. You should just choose the word period. But if you're at the start of a sentence, there are lots and lots of different ways to start a sentence. And so it might be that you want to choose from more options at the start of a sentence. And so Nucleus sampling, because it chooses a different K sub T at every step, allows you to have some more flexibility. And so this tends to work even better and generate better text when using top K sampling. And this is what I recommend if you want to control the amount of randomness in your text today. I recommend that you keep temperature and top K at their default values, and you just play around with this P value for Nucleus sampling. Yeah, I can say that one more time. So remember, for top K random sampling, you're picking a K, let's say 50, and you're at every step of generation, you just truncate the distribution to the 50 most likely words. When you're using Nucleus sampling, it's almost the same, except instead of truncating the distribution to the 50 most likely words, you truncate the distribution to the K most likely words, but form, let's say, 50% of the probability mass. So I've decided that every step of generation, I want to sample from the words that form 50% of the probability mass. So the K sub T most likely words that form 50% of the probability mass. Common values of P, I personally like to use 0.4, but that's kind of arbitrary. Something else to note, and you can play around with this in the practical component, is as language models have gotten better, and better and bigger kind of mean the same thing in the worlds of language models, as language models have gotten better and bigger, they've just gotten better at representing language. And so this means that the better of a language model you're using, the more randomness you can get away with, the higher you can set your P or your T for temperature, or your K for top K. So if you're using with like the latest and greatest of GPT-4, you can get high quality text with a higher level of randomness, of a higher value of P. But if you're using like GPT-2 medium, which came out 4 years ago and is just less good at representing language. All right, any other questions? Okay, I want to mention one more option, which is not very common for open-ended generation, but is still used in areas where there's like relatively few high-quality sequences, and this is beam search. So beam search operates under the assumption that the best possible sequence to generate is the one with the highest overall sequence likelihood according to the model. And this makes a lot of sense for areas like machine translation, where if you're translating from English to French, there isn't a space of many, many possible French translations. There's only like a few ways to translate any English sentence into French. And so because you have this sort of limited space of possible correct translations, beam search makes sense because you want to pick the highest overall possible, the highest likelihood overall translation. It makes less sense in like open-ended generation, like if you're like trying to build a chatbot, because in a chatbot, there's many possible correct things that the model could generate. So if you have kind of a limited task where there's only 1 or 2 correct answers, you might consider using beam search. Otherwise, you probably shouldn't. And so you want to find the best possible sequence, the sequence of the overall highest likelihood, but it's actually computationally intractable to search all possible sequences for a most likely one. So instead, we use this search algorithm called beam search. And beam search just approximates finding the overall most likely sequence. And I'm not going to get into the details, but I'm happy to talk about it later if you ask questions on the Slack. And so, as I mentioned, for like open-ended generation, beam search tends to be not very good because it generates text that's much more high likelihood than one a human writes. So here's sort of an interesting plot. I have 2 sequences here. One is the sort of the time step, which is that's just the position in the sequence. One is some text that was written by a human, and one is text that was generated using beam search. And you can see that when humans write things, they tend to alternate between saying things that are high likelihood and low likelihood. Like sometimes what I'm saying is really surprising. Sometimes what I'm saying is really boring because it's just like a common phrase in English. And so you get this orange curve that has a lot of peaks where you have things that are high likelihood and then a lot of areas that are low likelihood too. But text generative beam search tends to just have high likelihood stuff in it. And so it tends to not actually look like the text that a human would write. Yeah, so beam search does tend to write more boring text, which might be what you want for something like machine translation, where you don't want an incorrect translation. It's really important that your text adheres to the input sequence and your French text adheres to the English closely and doesn't just hallucinate things. And so that's the circumstance where like beam search might be practical to use. Yeah, if you want an example of boring text, you can look at the paper that I took this plot from. It's called, so maybe someone can find the link and put it in the chat, but it's called The Curious Case of Neural Degeneration. If someone wants to find the link and put it to the chat, that's where I should have put a reference on this slide, but that's where this came from. And so something else that we've observed, which I've called the likelihood trap, is, so I'm showing a plot here where we have the probability of a sequence, like the overall log likelihood of a sequence on the x-axis, and the y-axis is how well, what rating people gave this sequence. So we had a bunch of sentences that were generated, and we asked human raters, what is the quality of this generation? And we noticed this sort of interesting phenomenon that up until a point, as the likelihood of generated sequences gets higher, humans prefer them. But if generated sequences are too high likelihood, humans no longer prefer them. And I think this is one of the problems with like beam search or taking the Argmax, is you end up with sequences that are just too high likelihood. All right, so I've already sort of covered this. So in summary, there is sort of this decoding strategy trade-off. So I've talked about 3 ways to control random sampling. You can use temperature, you can use top K random sampling where you have this K value, or you can use Nucleus sampling where you set this P. But they're all kind of capturing the same thing, where you're trying to reduce randomness when you set them to low values, and you're trying to increase the randomness when you set them to high values. And so if you choose values that are too low, you can end up with text that lacks diversity and has an overrepresentation of common words, but it also probably contain fewer semantic errors. And so it'll look more convincing to a human, but because you have these subtle overrepresentations of certain words, it'll actually be easier for automatic detection systems to detect. That's just a fun aside. Meanwhile, if you set these values to close to their top value, so you're sampling close to the full distribution, you'll have text that has a similar diversity of word use to human writing, but it'll probably contain more like semantic errors that humans can pick up on. All right, so just briefly, here are a few other generation parameters that you'll encounter in the APIs that you'll use to generate. So I figured I would go over them. You have frequency penalties and presence penalties. So these are basically the same thing, but they reduce the likelihood of models generating a token that's been generated before. So if you're having issues with the model being like too repetitive and saying the same thing over and over again, you can use these penalties to get the model to be less repetitive. And as I said before, the bigger and better your model is, the less you might need these to generate high quality text. You'll also encounter stopping criteria. So this is something that we haven't actually talked about, is how do you stop generating? Like you could just say generate 100 tokens, but if you say generate 100 tokens, you might stop generating like in the middle of a word even, because we're using subword tokenization. And so you might want to have a better stopping criteria than just generating K tokens and stopping. And so you could do things like generate until you hit a period or generate until you hit a new line. And this is something that you can configure typically when you're calling into these APIs that generate text of language models. Someone asked, is hallucination related to some of the generation parameter, or it need completely remedy? I don't quite understand the question. So hallucination occurs when models give high enough likelihood to something that's like not true, that it'll generate that thing that's not true. And so there are two remedies. You can remedy this in just having a better model. So GPT-4 is going to have less hallucination than GPT-3 is going to have less hallucination than GPT-2. Because as models are trained for longer on more text, we just get better at knowing facts about the world. But also there's the issue where hallucination tends to occur during generation, when perhaps, let's say that you're asking how many legs does a dog have, and the model puts 80% probability on the word 4, because dogs have 4 legs, but it also puts 5% probability on the word 2, because maybe it's getting dogs confused with birds. And so there's a 5% chance that when you're using full random sampling, that the model might say that a dog has 2 legs. And so this is hallucination that's occurring not because the model wasn't putting high confidence on the true number of legs a dog has, but because you were doing random sampling, instead of choosing that most likely word, the word 4, you instead chose the word 2. And so that type of issue where you're choosing from the tail rather than choosing the most likely token does cause hallucination. That's the type of hallucination that you can reduce by using the right decoding strategy for your task. Yeah, so sometimes boring text is good. If you are building a question answering system, so a system that you ask just fact-based questions about the world and it answers, you really don't want hallucination. Hallucination is bad in a question answering system. And so in that case, you might choose to use Argmax, or you might choose to have random sampling with like the temperature or top K set very low. But if you're building a story generator or like a plot writer or a chatbot, you kind of want the model to say things that are like interesting and weird and might not be the most common thing. And so I can't give you like a single recommendation on what your decoding strategy should be, because it really depends on the task that you are building for. All right, so I see quite a few questions in the chat. I'll try to answer them. What would happen if the next word probability is 0? So the nice thing about how language models are trained is they never put probability 0 on any token. So it is impossible to have probability 0 on any token. You're always going to have some small non-zero probability. And this is what makes language models, neural language models, so powerful compared to the old statistical language models, is because neural language models do give probability to things we've never seen before. In fact, most of the text that you would say, like if you're having a conversation with ChatGPT, with high likelihood, the conversation you're having with it is something that it never saw in its training data, but it can still assign probability to the next word given the previous words. So in a model of high values of parameter KPT, can we expect higher hallucination than the average trade? Yes, that's correct. So someone asked, since the language models are trained on a finite number of limited tokens, can it not generate a completely new token? So yeah, so language models, so you have your, I don't quite know what usage of the word token you're meaning. So you have a vocabulary size. You cannot generate a token that's not in your vocabulary. but every token in your vocabulary is going to have some non-zero probability. And because you're learning this really, really complicated function, you are going to give probability to things that might not have been in your training data exactly, but are close to things that have been in your training data. For example, suppose I ask ChatGPT for a recipe for chocolate and mayonnaise covered shrimp. I'm pretty confident nobody has ever made a recipe for chocolate and mayonnaise covered shrimp. So that's not going to be in the training data. But because ChatGPT has been trained on recipes, it's seen recipes for things of chocolate, it's seen recipes for things of mayonnaise, and it's seen recipes for things of shrimp. And so because it's seen all of these, even though it has never seen this particular combination I'm querying for, it can put some probability mass on things related to all three of these things. And then what I'll end up getting probably is just a mishmash of all of the recipes it's seen before that have all of these ingredients in them. Someone asked, when you do prompt engineering, are you impacting the value of K and T? So prompt engineering is just what you're passing as that conditioning sequence. And so that's just telling the model, I have this prompt and I want it to influence the probabilities that the model predicts. That's completely separate from you choosing how to sample from those probabilities. So if we go way back to my slide with the figure of, sorry, let me scroll way back. If we go back here, so prompt engineering, you're just choosing this x sub 1 to x sub t, or if you're using a decoder only model, you're choosing this y sub 1 to y sub t. That's all prompt engineering is. But then you still need your sampling algorithm that chooses how to generate text given the probability distribution that your model has predicted. Does that make sense? So you can see that here. You can change your inputs, which are going to change these predicted probabilities, but ultimately you need to sample from those probabilities. Someone asked, if the parameters are set to give two boring outputs, could a question answering system lead to things like rephrasing the question? It kind of depends on how they've been trained. So this is something where like prompt engineering is impactful because it could be that your model doesn't understand that it's supposed to be answering questions. And so one of the things you might do with prompt engineering is pass in a bunch of examples of the model answering questions. And so it knows how to answer questions, like it knows the format of answering questions. And if you don't do that, it might just rephrase the question. Someone asked, there's no way to force the answer to be boring. Yeah, so the concept of boring, I've been using that word, but it's not a very good word to use because boring is a human judgment. You and I and everybody in this room has some concept of what's boring and exciting. But language models do not have that concept. The only thing that they have a concept of is text high likelihood or low likelihood? Is text surprising or not surprising? Where surprising is defined as, does it look similar to something that's seen in the training data, or does it not look similar to something that's seen in the training data? So text that looks similar to what's been seen in the training data will not be surprising to the model. And text that looks very different from what's in the training data will be surprising to that model. And so it'll get a lower likelihood. And so the concept of boring, I've been using boring to sort of mean like repetitive and doesn't have like weird word choices, which could be text that the model says is high likelihood, or it could be text that the model says is low likelihood. It sort of just depends. So I'm going to answer one more question and then I'm going to move on. I'll answer the question, what happens when we role play with GPT when we asked it to become a specific agent like an expert in a domain? Does it modify its model or selective context that it's trained on? No, when you're asking GPT to do these things, all you're doing, the only thing you're doing in this case is you are changing this input sequence. You are changing the y1 to y sub t minus 1. And by changing this input sequence, you are changing what probabilities the language model outputs, but that's the only influence. You aren't actually changing the weights in the neural network. And so OpenAI does have a way that you can fine-tune GPT-3, I think. And so like if you're using the API, you can fine tune it and actually change the weights in the model to make it better at representing your data. But unless you're using their fine tuning API, the only thing you are changing is this input sequence. Someone asked, how does fine tuning affect the generated output? Is it supposed to affect the last layer? What is this last layer? Yeah, so we're going to go into the architecture in a little bit. So yeah, fine tuning, the way that people used to do fine tuning is you have your model that has its millions or billions of parameters, and you updated all of them. And so you had a new copy of the model where every one of the parameters was changed from the original version, because your fine tuning was interchangeable with training. You're doing the exact same thing that you did at training, but just with some data that better represents your use case. So that's how people used to do fine tuning in the past. But this actually isn't great once models are hundreds of billions of parameters, because 100 billion parameter model is huge. It takes so many GPUs to load this in. Like, this takes a tremendous amount of resources. And so when you use the fine-tuning API, OpenAI's fine-tuning API, you aren't actually fine-tuning all of GPT-3. They have specified small subsets of the parameters in the model that are actually getting fine-tuned or actually getting adjusted in order to better reflect your fine-tuning data. And this allows for much better efficiency, because that means that if they want to support 100 different fine-tuned models, they only need a small extra amount of data being stored on the GPUs compared to if you had fine-tuned the full model. Yeah, someone asked, what can fine-tuning do beyond what prompt engineering can do? Fine-tuning, if you have data of the task you want to do, will almost always lead to better results than prompt engineering. Like, if you have sufficient data to fine-tune on and you have the resources to fine-tune, fine-tuning will almost always do better. Why would you not fine-tune then? One, fine-tuning is expensive. Even if you're only fine-tuning a small amount of the weights of the model, you still need to load the entire model into memory, or you need to pay OpenAI to do that. And so fine-tuning can be expensive. And also, fine-tuning requires you to have data for your task to train on. And if you have some like weird task that there's no data for, then you don't have anything to fine-tune on. And so that might be a case where prompt engineering is just better to use, because you don't need to collect hundreds or thousands of examples. Yeah, Gabriel also noted that if you can fine-tune, you don't need to manually design prompts, which is kind of nice, because like prompt engineering is kind of this weird magic that's difficult to get right. Someone asked, is there a minimum quantity of data required to fine-tune? People have fine-tuned on very small amounts of data. I've seen works that have fine-tuned on like hundreds of examples. Obviously, with anything in machine translation, the more data you have, the better you'll do. And mostly because if you're fine-tuning on small amounts of data, you just have to be really, really careful not to overfit. And so it can be like pretty challenging. Like, I remember at one of the projects I was working on at work, the code was set up such that the minimum batch size was 4. So the minimum number of examples that you could show the model at once was, I don't think it was hard, it was like 16, which meant that if you had 100 examples in your fine-tuning set, you literally did 4 or 5 steps of fine-tuning and you had covered your entire fine-tuning set because of the batch size of 16. And so it was really, really hard not to overfit. Someone asked a question about alignments. Yeah, we'll talk about that later. Someone asked, if I have private data, is this case suitable for fine-tuning? It depends. If you are using OpenAI's API, I don't think they make any promises to keep your private data private. I don't recommend that. But if you want to just fine-tune your own model on like your own GPU cluster you have, like, you can do that. And so that means you're just running everything on your own local machine. You're not giving your data to OpenAI that'll do big scary stuff with it. One of the caveats of this is that it's very easy, depending on the amount of fine-tuning data you have, to overfit, as I've said. And so I'd be a little scared that if you are fine-tuning on private data, you might overfit that private data, and people could do things like data extraction attacks, where they try to extract your fine-tuning data from the model that you've trained. For example, if you're training on social security numbers, like fine tuning on social security numbers, people might be able to extract a real social security number from your fine tuning data. Someone asked how to evaluate how much data is enough for a fine tuning task. Well, you should, this is just the same as all machine learning. So this is just a machine learning question. You should have a trained set that you're fine tuning data on. You should also have a validation set and a test set. And so you really just need to look at your validation set accuracy and see if it goes down and make sure that you don't overfit. So you don't like get perfect performance on your fine tuning data. And then you see your accuracy on your validation set go up and then back down. So it's just the same as any machine learning. Watch out for overfitting and make sure to have a withheld validation set. Someone asked, with a modern gaming machine, how long would it take to train a local 20K data set? I think that's totally reasonable. So the big issue is like the amount of RAM on your GPU. So if you have like a 16 gigs of RAM on your GPU, you should be able to fit the Llama 8 billion in and possibly fine tune it. You definitely, I think that might be like the largest model you could use. I think your limitation is really just the amount of RAM, which influences like what model you can fit in. But training for 20,000 steps should be pretty reasonable. It might take a few days, but yeah. Someone asked, can you comment on the performance of competitors of OpenAI like Llama? It really depends on your task. And let me actually just go on with my presentation because I'll talk about this a little bit more later. Okay, so we're running a little bit long. Do people want me to go over language model architectures or should I skip this? Okay, we got one yes. If anybody wants me to skip talking about this, all right. I'll try to go quickly because I know we want to have time for the practical component too. Okay, so language model architectures. I put these trapezoids in a bunch of the slides. So encoder-decoder, what do I mean by these? Well, first I'm going to talk about what was meant by these in the year 2013, because this actually influences a lot of how things work today. And so there was this paper, Generating Sequences of Recurrent Neural Networks, which was one of the first papers to do generation with language models, with neural language models as opposed to statistical language models. And let's look at how a recurrent neural network actually worked. So we're going to look under the hood of the decoder in a recurrent neural network. As mentioned in the last lecture, and earlier on in this lecture, the decoder takes as input a sequence of embeddings, y sub 1 to y sub t. The input sequence is then processed token by token. And so at each step of processing, we have this recurrent neural network unit that takes as input the hidden state from the previous step and the token, the y sub t being processed, and it updates the hidden state and makes a prediction for the next word in the sequence. So that's what I'm showing here. So let's just go through. So we have this hidden state that keeps getting modified by every step by the recurrent neural network. And so we'll just initialize it h sub 0, and typically you can initialize it with zeros or with a random vector. And you have this recurrent neural network unit that inputs the current hidden state and the token being processed. So you can see the arrows going into it. And as I mentioned, it outputs two things. It outputs a predicted embedding. So this is what we've already talked about on the previous slides. This is the predicted embedding for what we think the next token should be in the sequence. This is what you compute the loss on, the orange rectangle I'm showing here. And then it also modifies the hidden state and outputs a new version of the hidden state that's modified to take into account what it's learned by processing this token position. And so I visualized this recurrent neural network in an unwrapped way where I'm sort of visualizing it as like a sequence of things. But actually, every one of these RNN circles is the same thing. So this is it's just the same neural network. And so you'd really just have a loop. where you're looping over your sequence, and at every step of the sequence, you are making a prediction and you're updating your hidden state, and then you're going on. Are there any questions about this? Okay, so that's how a recurrent neural network works. And here is the text that was generated by that 2013 paper. So this was state-of-the-art text generation in 2013. And it's pretty good. You might notice, I mean, it's not pretty good by today's standards. 2013, this was pretty impressive. And you might notice that there are some weird words that I've highlighted but aren't actual real words, like artistitual and atticing. And that's because they used the character level tokenization. And so character level tokenization makes it so that things like this are more likely to be generated compared to if you're using like subword or word level tokenization. So that's why you get these weird words. Okay, so this is obviously not great by today's standards, and so let's keep moving forward. But first, this is something that is crucially important to talking about transformers, is we want to understand how in these encoder-decoder models did you connect the encoder of the decoder. And we're going to keep talking about recurrent neural networks for now because the techniques for connecting the encoder and decoder were mostly invented when people were still using recurrent neural networks. But what we're going to learn is going to be really impactful for transformers. So let's keep going on. Oh, someone asked, what about the loss function? So yeah, recurrent neural networks use exactly the same loss function. So the loss, let's just go back to this slide. At every step, we're still predicting this predicted embedding, and we still have the exact same loss function as before. Nothing has been innovated on in the loss function space, with respect to the standard language models, at least. Okay, so this is the plot I showed you at the very beginning, and we want to know how did the RNN-based language models connect the encoder of the decoder? Well, here is the dumbest thing you could possibly do. Your encoder is outputting a hidden state at every step. And your recurrent neural network and your decoder needs to have this hidden state that gets initialized somehow. Why don't you just initialize it with the last embedding, the last hidden state from the encoder? And so that's this dotted line here. So whatever the final hidden state from the encoder is, we're going to use it to initialize the decoder. This is very easy to do. But it's not actually a great approach because this means that you could have this really, really long input sequence, but all of that information in the input sequence is just being encoded in this single vector. And this single vector might be like 512 or 300 dimensional, which is not a lot of space to encode a really long sequence. And so a better approach is to use something called attention. And the attention mechanism is what forms the transformer we'll talk about in a little bit. And so let's consider the task of translation from French to English. We have a French sentence on the bottom, and the network is working on predicting the next word in the English sentence on the top. Clearly, some of the words in the French sentence on the bottom are more important for the prediction at this point than the others. And so what we're interested in for attention is how much should the neural network attend to each of the words in the input sequence in the French sequence when making its prediction at this point for the English sequence. And so you might get something that looks kind of like this, like the words "a" and "manger" in the French sequence are really important because we're trying to translate the verb, and this is the actual part of the French sentence that we are trying to translate. The words in the future, "mais" and "devoir," are less important because we don't really need to know what the object of the sentence is to make our translation at this position in the English sentence. And maybe the subject is a little bit more important than the object, but not much more important. And so you'll get some weights that look like this. Any questions? Okay. So these weights which are given to each word in the input sequence are called attention. And so in practice, for each position in the target sequence T, we want to produce this context vector. And the context vector, which I'm representing as C sub T here, that's the red box. is just a weighted sum of the final hidden states outputted by the encoder for each position in the input sequence. So remember, at each position in the input sequence, the RNN outputs a hidden state. So we have all of these hidden states, and we're just taking a linear combination of them and calling this the context vector. And so in the decoder, when we're making a prediction for position T, we use the decoder's hidden state, but we also use this context vector, which is like a summary of all of the hidden states from the encoder. And then we make our prediction for the decoder based on both of these. Someone asked, how are the attention weights generated? That is my next slide. So there's been various methods proposed for choosing these attention vector. So I'm going to use attention vector to refer to a vector that just has the attention weights for each position in the encoder. The simplest method that tends to work pretty well and works basically as well as more complicated methods is just to take the dot product. So this is very standard. So so suppose that you are currently at position T in the decoder. You're trying to come up with an attention vector for position T at the decoder. You have your hidden state at the decoder at position T, and you take the dot product of this hidden state with every one of the encoder's hidden states. And so you have the dot product of the encoder hidden state 1 with the decoder hidden state T, the dot product of encoder hidden state 2 with the decoder at T, and so on. And so these are just the weights that you use, your alpha sub 1 to T. Any questions? So one of the more complicated things that people have tried is adding like learns parameters in here. So you might have like a weight matrix that gets learned in your attention, but that tends to not work much better than just doing this. Okay, so one of the things that happened in 2017 was this paper, Attention is All You Need, which had the brilliant insight that this attention, which was originally invented as a way to connect to the encoder to the decoder, was actually really, really powerful. And you could use it even within the encoder or within the decoder to just connect the encoder to itself, to have different layers in the encoder where sequences were just paying attention to themselves. And if you did this, you could actually drop the concept of recurrence, not have a recurrent neural network at all, just have attention layers and get a model that worked really, really well. And all modern language models now basically use this transformer architecture. So transformer is the T in GPT, general purpose transformer. So one of the issues with recurrence and why people wanted to drop it is it actually makes neural networks really slow to train. And this is because the computation cannot be parallelized. The computation at position T is dependent on doing the computation at position T minus 1. And so this meant that it just took a long time to train a lot of data. Also, recurrent neural networks do poorly with long context. So if two tokens are k positions apart, there are basically k opportunities for knowledge of the first token to be erased from the hidden state before a prediction is made at the position of the second token. So this meant that if you needed knowledge from the very beginning of the sequence to make your prediction, it would have had to have been just kept around in this hidden state that's been modified and modified and modified. And what ended up happening is that just the context from the beginning of the sequence would tend to get lost. And transformers solved basically both of these problems with recurrent neural networks. So here is the picture of the transformer architecture from the original Attention is All You Need paper. We're going to end our discussion of architectures by sort of going over this picture to try to understand what's actually going on here and how it fits into everything else we've talked about before, or we've talked about already. Okay, so you have your encoder. This is what we've seen lots of times already. You have your decoder. Again, this is what we've already seen. This part of this picture here is exactly what we've talked about already, where you have your embedding matrix and you are using it to find the Logits, which is a score for each item in your vocab, and then you're taking the Softmax on this to get your output probabilities. So that part we've seen before. And this is a part that's a little bit different from what we've seen before. So one of the big differences between recurrent neural networks and transformers is that transformers don't operate on variable length sequences. And so you need to have basically this input matrix that we pass as input to the encoder. So we form this matrix by just taking the vocab items, the embeddings for each of the vocab items, and stacking them together. And this is what you see on the left here. And if you have a sequence that is too long, you have to truncate it to whatever your sequence length for the model is. And if you have a sequence that is too short, you have to pad it because the transformer requires that it has an input that is of this dimension for all the matrix multiplications to work, which is different than recurrent neural networks, where you could sort of train on sequences that had different lengths because you were just iterating basically over the sequence for as many tokens as it had. And one other thing that had to be done for transformers is attention doesn't actually have any knowledge of positions in the sequence. So remember how we're taking this linear combination of all of these embeddings. So you have an embedding for each position in the sequence, and you're just taking a linear combination of them, which means that you don't actually have any position data, like that the word the is in position 0 and the word dog is in position 5. That is not encoded in the attention operation. And so how to resolve this is you actually have these position embeddings that you add to your input matrix that are just like these slow synodal shifts over time. And you can use this to distinguish between, or the model can use this rather to distinguish between tokens that are early in the sequence and tokens that are late in the sequence. Any questions so far? Okay, so this is the H sub 0. This is the input to the encoder. And so now the primary component in this transformer that makes it work are all of these attention mechanisms. And as I already mentioned, one of the innovations in the transformer compared to the attention that was used in these old encoder-decoder models, the recurrent neural networks, was to have self-attention. So have attention where sequences attended to themselves. And so first, let's just show you this one here, but I've highlighted. This is the encoder-decoder attention, this one here in the graph. And you can see it because it has an arrow that comes from the encoder that goes into it. So this is exactly the same as the attention we saw in the recurrent neural network. But then you also have these self-attention layers where you basically have a sequence attends to itself. And so you'll get things that look like this. And I'm showing on the left, like a couple of the attention, like where the weights look like. And you can see the one on the left isn't so meaningful, but the one on the right, you can see that like words are roughly attending to the last word in the clause. And so some of the attention heads tend to be informative, like the one on the right, but most often they look kind of just random, like the one on the left. But that's self-attention. One other thing that you'll see here is the word masked. You'll have masked self-attention. And this just means that in the decoder, when you're doing the self-attention, you don't want to attend to words that are in the future, that are like later in the sequence than the current position you're processing. Because if you do, you won't be able to do generation. So at inference time, you don't have knowledge of the future because you haven't generated yet. So masked self-attention just means that you're masking out tokens that are later than the one you're currently generating. So you can see that here on the left with the colors. So there is a darker color means that there's a higher attention weight going to this word. And you can see that everything is white below the word that we're currently computing attention for because we don't want to attend to the future. Okay, and then the last thing to briefly mention is this word multi-head, multi-head attention. And this just means that each attention layer consists of multiple attention heads. So instead of just having one alpha at this attention layer, you have 6 different alpha. You can see them in the different colors here, or maybe it's eight different alpha. So these are just different attention heads, and this allows the model to just have more learning capacity, basically. Someone asked, can you explain the key value query and what they are in this example? How does it relate to X and Y in the sequence you mentioned before? Yeah, I ended up removing those slides to try to save time, but let's talk about that on Slack, and we can I can point you to some resources to try to understand the key query and value. All right, any questions? All right, so I'm gonna kind of go through this last bit quickly because I know you all want to get to the practical exercise. So this is typical pre-training data. So most language models from all of the big companies and all of the open source models are just trained on web documents that were scraped from the web. And these are two pretty typical web documents. So I went to this website, c4search.apps.ai.org, and you can go there. C4 is like a very common training data set for models. I'm pretty sure Llama was trained partially on C4. And in this case, I searched for Pittsburgh Penguins, and I just took 2 of the random articles on it. And if you read through these, they don't look very good. They're pretty noisy, and they just have a bunch of random text in it because this is HTML that was turned to text, so they're not that good. And so one of the issues we have with language models is that there isn't very good alignment between what the pre-training data looks like and what users want to ask the model to do. So here are 2 just random documents about the Pittsburgh Penguins that I found in C4. But what a user might want to do is ask how many times have the Penguins won the Stanley Cup playoffs? Or if I might want to ask the model to summarize an article about yesterday's game, or if I might want to ask the model to translate the article from English to French. And users also want models to avoid swearing or like generating offensive content, or possibly like hallucinating a winner for the 2024 playoffs that haven't happened yet. And so one of the fundamental questions is, how do we go from a model that was just pre-trained on all of this giant amounts of web documents, which are kind of low quality on average, to a model that can do these things that users want them to do and avoid things that users don't want them to do? And this is called alignment. So when people talk about alignment, that's what they mean, is getting models to be good at the tasks that humans want them to do. And so in the past, people tended to do task-specific fine-tuning. And so you would collect like a fine-tuning data set for the task that you wanted your model to be good at, and then you would fine-tune on that task. So people did this for tasks like question answering or summarization or translation. But there's several problems with this approach. One is that this results in a lot of models, 1 model per task. If you have 50 tasks, suddenly you have 50 models, which is maybe fine if your models are really small, but is not something OpenAI can do if their models are like hundreds of billions of parameters. And also fine-tuned models can be unintuitive for non-technical users. For example, a fine-tuned model might expect the input to be in a very specific format, and if you deviate from that format, it won't work as expected. And finally, what do you do if there is no readily available training data for your task? So humans are often able to complete tasks that they've never seen before if they are given instructions on what to do. We don't need, as humans, hundreds or thousands of examples of a task in order to be able to do it. And so this led to sort of the innovation that we don't need to fine-tune for specific tasks. We can just sort of fine-tune for alignment in general. So we can train on data that encourages the models to be aligned with how users want to use them or how the model creators want us to use them. For example, like OpenAI will not give you instructions. Their models will not give you instructions on how to make a bomb, even if you want instructions on how to make a bomb. So when you're fine-tuning for alignments, you fine-tune for goals like instruction following, or being conversational, or avoiding problematic topics or toxicity. And it turns out that if you fine-tune for the goal of instruction following, you get a model that can do question answering or summarization or translation, because doing those tasks is just following an instruction from a user. And so this is why sort of fine-tuning for alignment has become the dominant approach that people have been taking. And so you'll hear people talking about like RLHF, like reinforcement learning with human factors, or you'll hear people talking about instruction tuning. I would put all of those under this category of fine-tuning for alignment. So as I mentioned, fine-tuning is necessary because we train on internet data because it's the largest source of natural language, but it doesn't look very natural on aggregate, as we saw on the previous slide. So what model should you pick for your task? Well, the first thing you should do is you should research the data a model was pre-trained and fine-tuned on. Most people who release models release something called a model card, which is like a kind of a brief 1-page summary of their model and everything you need to know about it. So you should read the model card. It'll tell you what the model was trained on. It'll tell you what the intended use case of the model is. So you should definitely read that. And then you should decide, do the model's creators' goals align with your goals? And if they do, then maybe this is a reasonable model to use. And then for efficiency reasons, you should also try to like figure out what is the smallest model size you can get away with. Like maybe you don't need GPT-4 to do your task, and that GPT-2 or the small versions of GPT-3 might work just as well for your task. And then I want to end with this point, but there is no one-size-fits-all model. As some examples, like for example, if you filter out toxic text during pre-training, so you filtered your pre-training data set to not have any toxic text in it. Well, this is going to result in a model that is unlikely to generate toxic content, but it's also not going to be a very useful model for the task of toxic speech detection. And so there you have a trade-off. Or as another trade-off, multilingual models are often worse at each individual language than a model that's like trained just on English or just on Chinese. Or as another example, a model trained to have a particular persona like ChatGPT or Bard is going to be worse at generating text in alternative voices and styles. Okay, so I might answer some questions in the chat and then take a 5 or 10 minute break, and then we will go to the practical exercise. Someone asked, how do each of the multi-attention heads learn different things? I wouldn't say it's like, it's sort of by random, but it's basically, yeah, you have these weight matrices. So I didn't go into too many of the details, but you have your input to the attention layer, and you basically transform it using a weight matrix. So you have 6 different transformations of your input, and those weight matrices start off randomly initialized. So yeah, there is some randomness there. And so you have these 6 different transformations of your input, and you compute the attention on each of those 6 transformations of your input, and those give you the 6 attention heads. Someone asked, how do you determine the dimension of the embedding matrix? How do you know it is sufficient? As a practitioner, you're probably just going to use whatever the models that you find online use. So this is not like, unless you're training your own model, you don't really have a choice over this. I think that there's like some conventional wisdom in this from like also like empirical studies about what works. Typically the embedding matrix will have like a dimension of 512, sometimes 1024. It just depends on how big of a model you want to have too. Like the bigger your embedding dimension is, the bigger your model will be. It's like, if you look at the different T5 models, for example, like the smallest T5 is going to have a smaller embedding dimension, the biggest T5. I thought you can ask ChatGPT to take on a particular person, speaking as if it's a Legion art critic. Yeah, you can, but I found it doesn't work especially well. And the more you ask, the more of it the person you wanted to take on deviates from the alignment that OpenAI has trained its model to have, the harder it will be to get it to take on that persona. For example, if you wanted to take on the persona of a serial killer, that's probably going to run up against the alignment fine-tuning that OpenAI has put on its models. Yeah, so the link to the collab is here. And let me copy and paste the links to the Slack channels if you're not already in them. Okay, let's take a 10-minute break, and then I will come back at 1 o'clock and we will go over the collab together. Feel free to start playing around with it yourself too before then. All right, I think we're gonna get started again. So this next hour is going to be mostly self-directed. I'll just give a little bit of I'll just give a little bit of details on how to get started. Okay, so we have this collab, which we have prepared for the purpose of this tutorial. If you haven't used collab before, it's basically a combination of text that you can read and code that you can run. And it is being run on Google's cloud server. So you don't need to actually like create a Python runtime yourself. So to get started, you just need to press this button at the top, which will say for connect or reconnect, one of the two. And then that means you're connecting to a runtime that is on Google Cloud. And then once you're connected, you can read various things, but the two crucial things that you need to run to get started is you need to run these important initialization, which you run by pressing the play button, as you can see what I did that was on the left of this code block. So the collab is just a mixture of two different types of these blocks. You have text blocks, which obviously don't run, they just have text, and you have code blocks, which you can press the play button next to run. And as this is running, you can see the outputs below, so you can see exactly what's happening. Right now, I'm just installing all of the things that you need for this collab. Okay, so that's important thing number one to run. Important thing number two to run is there's lots of different APIs for language models, as we've talked about. And we've tried to make things easy for you guys by taking all of these different APIs that exist for running language models and giving them a common interface. Oh, my mouse pointer is not visible, so I apologize for that. So I will try to do a better job of just saying where I'm clicking. So yeah, we tried to give all of these different models a common interface, and you can see that interface here. So the two functions we'll be using for this tutorial are a score function that takes text and gives you the log likelihood of each token given the tokens before it. So these are just the scores in that Logits vector. And also a generate function that generates text from a prompt. So this is what you do to do generation. All right, so in order to get started, you need to press the play button next to this engine interface, and this creates this interface. So once you've run those two code blocks, now you need to pick which language model you want to use for the tutorial. I'll briefly summarize the options we've given you, and then you can pick based on them. First, we have GPT-3 with OpenAI's. This could cost real money, so they may, I don't remember if OpenAI asks for your credit card, but it might. So just as a heads up. OpenAI are like the latest and greatest state-of-the-art large language models, and they definitely have like the lion's share of the market on large language models right now. I've also given you code to run a competitor of OpenAI called Cohere. This one will also possibly ask for credit card information. You might need to use real money, but it is fairly not very much money. It costs $15 to process 1 million tokens, and this tutorial will probably process on the order of like 1,000 or 2,000 tokens. So then if you choose to use either OpenAI or Cohere, your max going to spend maybe $1 on this tutorial, but I just want to give that heads up. So Cohere is a little bit more transparent about their models than OpenAI, which is one reason why you might choose to use their models over OpenAI's. Yeah, moving on then, so those are both closed source models, but we can also talk about the open source models. And so the most common way people run models in the open source world is with this software package called Hugging Face. And so you can load hundreds of different models of Hugging Face. We're giving an example of just 3 that you can try with Pythia, GPT-2, and Bloom. So you can choose which of those you want to do. If you don't have a preference, I would just keep it at Pythia. And finally, the state-of-the-art large open source model right now is Llama. Unfortunately, Llama is too big to fit into this Colab runtime, into the Google Cloud runtime that you're given. And so instead, we have created a server that's on the LTI compute cluster. And so if you want to run the open source Llama, you can use the server that we have on the LTI compute cluster to use the latest and greatest of open source language models. And those are the instructions here for that. Okay, so y'all should pick which of these you want to do, try to get it working. And if you have any issues, from this point forward, if you have technical issues that you want us to help debug, it's better to post on the Slack. I'll be monitoring the Slack more than I'll be monitoring the Zoom chats. Yeah, so Greg says that the tutorial stuff cost about 25 cents using the OpenAI API. Yeah, that's correct. So run the import and then run the interface first, and then you can pick which of the 4 models you want to use. Of the ones that are marked pick one, you don't need to run all 4 of those. You should pick the one that you want and just follow the instructions for the one that you want to use. if you don't have a strong opinion and you don't care about like possibly needing to give your credit card information, I recommend just using OpenAI's models because that'll work pretty consistently. If you're super into open source, you should pick either Llama or one of the other models that you can load on Hugging Face. If you want a state-of-the-art money, but you're anti-OpenAI, state-of-the-art model, but you're anti-OpenAI, you can pick Cohere's models. Oh yeah, you might get a warning saying that this collab is sketchy because it's from GitHub. Just press OK and ignore it. You have my guarantee that it doesn't do anything sketchy. Yeah, feel free to pipe in on, like, turn on your mic and pipe into it if you guys have any questions. I'm happy to help. Debug. Maybe you can put a thumbs up in the chat if you have gotten to the point where you can try getting to 1.2 and running this engine.generate in 1.2, this block here, and maybe give a thumbs up in the chat if you're able to get generation working. Also, if you guys get any funny generations or things you want to share with the rest of the class, please do just take a screenshot and post it in the tutorial to discuss Slack channel. Someone pointed out that Hugging Face called a hippo a long-necked mammal. Yeah, that sounds like a good example of hallucination or of the model getting things wrong. Something you can experiment with if you're getting weird generations, like the hippo is a long-necked mammal, you could try taking this top P parameter, which is set to 1 currently. And if you set it to something closer to like 0.1, you're probably less likely to get weird things. Let me. So if any of you have gotten to analyzing likelihoods, I think this is particularly interesting as doing this. You should try out a lot more sentences than just the little "it's raining outside." It's trying to look at the token scores, so these log likelihoods of the tokens, to try to understand when they're high and when they're low, like what kind of text does the model feel confident about and what type of text does it feel surprised about. And I think these are super interesting to try to understand because they give you an insight into like what the model is thinking, what the model thinks is confident, is high likelihood, and what's not high likelihood. So like you can see here that in the sequence, it's raining outside. The word outside is very high likelihood given it's raining, which makes sense. But then if you have a typo, you get something that first of all gets broken up into more tokens because the typoed word is not in your vocabulary. And it actually starts off sort of high likelihood because out makes sense, but then outside, where there's the typo, does not make sense. And so it jumps up in likelihood to get the last part of outside. Okay, so if you're getting rate limit errors for GPT-3, this just means that too many people are trying to use it at the same time. So one thing you can do is try to use a smaller model, which will probably have fewer people using it. So in this GPT-3 run block, you can go, I don't know if you can see, I think you can see, if you click on model name on the right at this dropdown, you can switch it to like query, text query 001, and then rerun this code block of text query 001, and that should get rid of the rate limiting errors. You can also upload your credit card information. I don't remember the instruction to do it. It should be, if you follow the instructions we put here, there should be a way to do it. Let me know if you need help with that. Someone asked why is the tokenizer breaking words into parts? So this goes back to the subword tokenization that we were talking about. So in an ideal world, every word in English would be a token in your vocabulary. But you can't do that in practice because our vocabulary needs to be finite sized. And normally you choose something like 50,000 or 32,000. And so in order to represent every word in English of just 32,000 or 50,000 tokens, what you end up doing is each of your tokens for like really common words like apple, that might be an entire token. But for less common words like raining or outside, it could possibly separate it into multiple tokens. So you might get rain being a token and ing being a token, and then they get concatenated together. And so having subword tokenization allows you to represent more of your language, like more of English, using your budget of 50,000 tokens than you would otherwise be able to do. Regarding the poem perplexity, someone noticed that the values are really big for the Hugging Face models and really small for the OpenAI ones. I think there is a normalization bug in our Hugging Face. Like the perplexity scores we're getting for Hugging Face, I noticed this morning, but didn't have time to fix it. So notice if you're using the Hugging Face models, you're going to get like very large perplexity values. I'm pretty sure that's a bug in our code that we're not normalizing correctly. So the relative scale of the numbers is correct, but the numbers are the wrong overall scale. So I'll fix that for tutorial 3. I only noticed it this morning, so I haven't had a chance to fix it. Yeah, someone says that for llama, the perplexity of poem A is much higher than poem B. That might be due to the bug. That shouldn't be the case. Let me try doing that to see what you're seeing. So this is what you should expect, is something like what I'm showing here, where the actual version of the Jabberwocky poem should have very low perplexity because it's almost certainly in the training data. In my weird version where I modified the poem, that should have pretty high perplexity because it's something random that I wrote a week ago. But let's see what we get with the llama models. Yeah, I think there is a bug in my perplexity computation, and sorry, I will fix that for next week. Yeah, an interesting observation of some of these weird outputs is if you're using Hugging Face, you're using a fairly small model by today's standards. I think the default that we're loading in is Pythia 1 billion. And so these sort of like wonky generations, like a Yorkshire Terrier having health insurance, are actually more common on the smaller models than on the bigger models. And so I was doing a research project last year where I was working with professional writers, and a couple of them said that they actually preferred working with smaller language models than larger language models because they want the language model to make suggestions which are just like wonky and weird. And the larger a language model is, the less likely it'll say things that are wonky and weird because those things it'll learn, those things are not in the distribution of normal language. It'll be less likely to do them. Yeah, are people still running into rate limiting with GPT-3? I can't run step 1.2. Okay, let's look at step 1.2. Can you paste, if you're getting any errors, please just paste a screenshot of your error in the Slack. That makes it easiest for me to debug it. Yeah, someone posted in the Slack, a bunch of the generations are incomplete sentences. And this isn't something that you need to fine tune the model to avoid. They're incomplete sentences because you're asking the model to generate K tokens, like 10 tokens or 15 tokens. And if it ends generating 15 tokens in the middle of a word, it's just going to stop generating. And so the way people get around this in practice is generate more tokens than you need and just truncate it to the end of a sentence to a period or something. Yeah, please post on the Ask a TA if you have technical issues, post screenshots there. So it's tutorial 2-ask-a-TA. So we covered what reducing the top p-value actually does in the lecture. So this just limits the number of words you are sampling from. So it says, if your p is lower, I am gonna choose from fewer possible words than if p is higher. If p is 1, you're choosing from all 50,000 words in the vocabulary. If p is close to 0, top P is an extension and it's improvement on K. So top P is saying instead of picking 1K and using it at every step of generation, I'm going to choose a different K at each step of generation. such that I am at each step choosing from the P% of the probability mass. So think of it as very similar to top K, except in practice, it works a little bit better. Yeah, if anybody is still having issues with the OpenAI code, please let me know, and we can try debugging it together. Yeah, so if you go to the link for OpenAI that's on step 2 in the OpenAI instructions, and you click on it, and then you can go to billing and add a payment method. This should hopefully resolve things for you so that you stop getting rate limiting errors. And if it doesn't, just post on the Slack and we'll try to figure it out. And make sure to post on the chat. Sorry, go on.
Sorry, I did that. I add the payment method, but still not. Maybe I need to regenerate the key.
Yeah, you could also, you could try creating a new key, and that might help.
Okay, thank you.
You can see that I have a lot of temp 2, temp 3, because I always forget my keys and just make new ones.
It took about 2 minutes before my payment method was recognized.
And just as a note, if you are concerned about accidentally spending $1,000 or whatever, you can just set a limit. But I've been running this collab a lot over the last 2 weeks since I was developing, and I've spent a total of $2.34. So it's actually pretty cheap for the type of usage that we're doing. Julia said she noticed that reducing top P to 0.1 made my samples very repetitive. Yeah, so which could be good if you want your samples to be repetitive, but if you're trying to generate crazy dragon names, then maybe you don't want them to be so repetitive. Someone asked, is the score function we're supposed to return likelihoods from a next token after the prompt, or the next token or the last token in the prompt? So what the score function does is it takes a sequence of text, it tokenizes it, and then for each token, it returns the probability, the log probability of that token given the previous tokens in the sequence. And so that's why you'll get the same number of scores as output as tokens in your input sequence. Yeah, I think there might be a bug in the perplexity computation for the open source and llama models. Let me try playing with it. Okay, so let's look at these together. So this kind of makes sense to me. So the word outside is very likely given it's raining. And so it has like, that looks like -7 or so. And let's scroll down quickly to the other one that it's raining dragons. And you can see that the start of the word dragons is -10 compared to -7. So the word dragons is less likely given it's raining than the word outside. Things get a little bit confusing here when you start with, when you have the typo word, because a typoed word gets turned into 3 tokens, oust, ide, out, assist into ide. And maybe it's raining out there, like there's other things that start with OU that are likely. So that's why this OU token is actually quite high likely given it's raining, because maybe there are other probable things that start with OU. Yeah, I don't have recommendations. If you've created too many OpenAI accounts with your phone number, you should just try to find your existing OpenAI accounts and use them, I guess. Yeah, the example that Sung put in the chat of the different p-values is pretty informative, I think. You can see that when p is really low, you get text that is pretty boring, like, she was a beautiful fairy. She had a very large data center. She had a lot of data center friends. But when p is high, you get text that's a lot kind of more interesting. And then when I ran it earlier today, I got a fairy named Sysedmin who had been around since the first computers. All right, sounds like generating a new API key works if you're having issues of OpenAI. Is there a maximum value of perplexity? No. You could pass in text that you think is like super unlikely, like just like gibberish, and see what the perplexity is. But as a note, I think there's a bug in our perplexity computation for llama and the Hugging Face models. So if you want to investigate perplexity more, you should try to use either OpenAI or Cohere's models. And just experiment with like spamming text on your keyboard and seeing what the perplexity is. Okay, so Sung-chan asked, for in-context learning, I'm stuck with the old paradigm of programming. If all we can do is let it generate the next string of words, how does it help it learn? So yeah, so remember that the transformer architecture has this attention in it. So it's basically choosing what to output based on attending to everything in the input sequence that it's given. And so by passing in an input sequence that has like instructions on the task you want it to do, the model can now attend to those instructions and use some representation of those instructions in order to make its prediction for the probability of the next token. And so that's really what you're doing, is you're altering the probability that the model predicts by allowing the attention weights to focus on other context things that you've passed in. Ingo asks, will the notebook work outside of Google Colab? Yes, you don't need to use Google Colab. We just did it to make it easy. So you can read this in the top code block, but so Google Colab is just a version that's of IPython notebook that is hosted by Google. So the server that is running on Google, but you can use one of these notebooks called an IPython notebook running on your own personal laptop if you wanted to, and that's completely fine. So if you want to do that, you just need to go file, download the IPython notebook, and then you can run it locally too. Yeah, I think a lot of people find it bewildering that any of this works. So you're not alone in feeling this way. I'm bewildered at how well it works sometimes. Yeah, in response to Andrew Liu on Slack, I think there might be an error in how we are computing perplexity, because that does seem weird. The numbers shouldn't be that different from each other. Something you can try doing is just print the sum of the scores. So you can just do like np.sum poem a scores and print that out, and that might give you something that's easier to interpret. I don't think 0 is possible. You should never get a perplexity that is 0, because you're taking either e to the scores or 2 to the scores, so like you can't get 0 from that. Yeah, so this translate English to Chinese example, some of the language models we've given you access to are multilingual and some are not. So that might not work depending on which model you're using. I think if you used Bloom, it probably would work because Bloom is multilingual. I think GPT-3 is also sort of multilingual. But like the Pythia deduped, this one here is only English. So that's something to consider. If you want your model to be able to do translation, you probably should pick one that was trained on multilingual data. I think that GPT-3 was trained on some multilingual data of the open source models. I think the only one we've given you access to in this collab, and you can always find your own, but the only one we've loaded in is Big Science Bloom 1B. This was trained multilingual data. But if you go to the Hugging Face website, there are many, many models here. So you can go and find one that best fits what you need. If you want text generation, you can click on that. I think there's a way to pick language too, if I remember. But you can just go here and see what else exists in the world. Yeah, perplexity is kind of weird, or just likelihoods in general are kind of weird because they tell you how confident a model is that something looks like its training data, looks like the model's training data. But that it doesn't always work in the ways you expect it to, because something can look like the training data because you trained on English and this is fluent English. And so you will get high likelihoods because it looks like fluent English. Or you might get high likelihoods and low perplexity because something just happens to be in the training data 1,000 times. If I take a gibberish string and it's complete gibberish, I made it up, and I somehow convinced OpenAI to put this string in its training set 1,000 times for its future versions of GPT-4, then that string is going to have very high likelihood and very low perplexity, even though it's gibberish. So likelihood gives you some sense of what sounds like English, but it can also be fooled by things like overrepresentation of certain text in the training set. I don't think there are any models trained specifically on educational texts. There might be models that have been pre-trained on a bunch of stuff and fine-tuned on educational texts. You would have to just look that up. I do think if you look up what Llama was trained on, I'm pretty sure Llama was trained on all of Stack Overflow. And so I don't know if you count Stack Overflow as educational text, but if you do, then yes, that was in its training data. Yeah, so for the sentiment analysis, that was just our example of training a classifier. So if you look at the input data, let me bring that up. But the input data has these labels 0 or 1, where 0 means this is negative sentiment and 1 means that it is positive sentiment. One way to get models to do better at tasks like this is to find label names that might have more semantic meaning than 0 or 1. So you could keep the labels as 0 or 1, but empirically people have found that your classifier using these few-shot learning techniques will do better if you pick label names that look more like things that are meaningful. So that's why we have this label map to turn the 0 and 1s into positives and negatives. Have there been experiments with using larger semantic units than words, for example, sequences of instruction steps? Yes, there has been some research on using larger tokens than words and subwords. None of the state-of-the-art models have adopted it yet because it just becomes really tricky because like you very quickly run out of budget. If you only have a budget for 50,000 tokens, you need to decide what phrases are worth including in that budget, and that can be tricky. So I would say that this is an active area of research, but not something that state-of-the-art models are currently doing. Okay, so text summarization can be framed either as a generation task or as an extractive task. So in the past, when people did summarization, they treated it as an extractive task. So you have like a large news article, let's say, and you want to extract a subset of the sentences from that article, which summarize the article. So what are the most salient sentences in the article, which basically summarize everything that's in there? That's called extractive summarization. The other way you can do summarization is called abstractive summarization. And this is where, given a news article, you want to generate a summary of the news article. And your summary might contain completely new sentences that are not in the news article because it might like combine sentences that are in the article. And that is generation because you are generating new sentences. But ideally, you want your generation to be shorter than the text that you are summarizing, as otherwise it isn't a summary. Then you'll notice that it's raining cats actually more likely than it's raining outside. So I guess it's raining cats and dogs is a pretty common sentence. But normally when you're saying it's raining, you don't need to say outside because that's sort of redundant. That's a good instance of what you think is more common, like it's raining outside, is not necessarily what was more common in the training data. Okay, so generating an extractive summary, that's sort of like an oxymoron. Like an extractive summary is precisely not doing generation, it's just extracting sentences. So if you are using a language model to do summarization, you are doing abstractive summarization because you are generating text. There's other types of machine learning models you can use to do extractive summarization, but we don't cover them in this collab. Actually, I want to correct what I just said, because one thing you could use, use a language model for doing extractive summarization is you could look at the likelihood. So you have your news article, you want to summarize it using extractive summarization. So just taking sentences from the news article, you could do something like compute the likelihood of each sentence in the text and like pick the sentences that are highest likelihood or whose likelihood is most similar to the title, or there's like things like that you could do in order to get some signal to use for extractive summarization. But if you're actually generating text of the language model, that now becomes abstractive summarization. So Sung-Chan said that in the sentiment analysis, it's pretty bad at guessing compared to the 0 to 1 already provided. I'm not quite sure what you mean there. So let's look through this section together. So first we're loading some data. One reason, by the way, why you might want to run your IPython notebook locally on your personal laptop and not on Google's cloud is if you run the cloud, you need to re-download your data resources every time Google decides to kill your runtime and says you've had enough time. But if you're running it locally, your resources get downloaded on your local laptop, and you don't need to do this every time. Okay, so I just downloaded my data by running this code block. Here are 3 examples from the training data. So these are not examples where I made a prediction. These are just examples in the training data. So now we are going to form a prompt from examples in the training data. So this is our few-shot learning prompt. And you can see that it has 4 examples in it, 1 positive, 3 negative. And you can play around with this if you want. You can try like changing the random seed to get 4 different examples. Or you can try, instead of negative and positive, you could be like, you could replace these with good, bad, and see how that impacts how well the model can do this task. That's something that you can play around with. Or you can just keep them as 0 and 1, which I think will work worse when using good and bad or positive and negative, but it is something that you can try doing. And that's because 0 and 1 are less semantically meaningful for this task when things like good, bad are positive, negative. Okay, so anyway, here is my prompt. And now I'm going to evaluate how well that prompt worked. All right, so we got a question. So Yelp reviews are already stored in the training data. If we want to classify video transcripts as positive and negative, but we do not have training data for it, can we get good results of generator? So this is using few-shot learning. So there's probably Yelp reviews in the pre-training data for a large language model, and there's probably also video transcripts in the pre-training data for our large language model, just because large language models are trained on tons and tons of data. So what we're doing here is not any extra fine tuning or anything. What we're doing is we're just grabbing a data set to evaluate on. So we're not doing any fine tuning. We're just grabbing this data set so that we have something to evaluate on. And we could have manually written our own few-shot prompt. If we had wanted to, I could have crafted a bunch of reviews and made my own few-shot prompt. But instead of doing that, because I'm lazy, I just took 4 the reviews that were in this training data set. So I'm not actually training on this data set, but I just grabbed 4 reviews from it in order to form this prompt. So I'm not actually using the training data set for any training. I just used it in order to generate this few shot learning prompt. And if you don't have a big training data set, you could have written the prompt manually yourself. But because we did happen to have this training data set, I just loaded this in. And then for the code block that does evaluation, all it's doing is just prepending this to the reviews that you want to classify and doing that on each of the reviews and then getting the predicted sentiment of that review and then computing accuracy. But it looks like I had an out of memory error. What was the final accuracy? So if you run that code block that computes validation set accuracy, what accuracy did you get? When you're saying the predictions are often wrong. There will be a recording. So we're giving 3 of these tutorials. We're going to pick the best one. They cover basically the same material, and we'll record the best of the 3 and put it online after all the tutorials have happened. And I'll also share my slides at some point soon. All right, that's surprising that you got 50% accuracy. Yeah, I don't know what's going on with that. I'm running it right now, GPT-3, and I'm guessing I'm going to get probably like 80% accuracy at least. You can take a look at your prompt to see if your prompt was balanced. Like, did your prompt have the same number of examples with positive sentiment as negative sentiment? If that wasn't the case, you might want to like rewrite the prompt a little bit. Yeah, going back to the one example someone posted in the Slack, which was kind of interesting, where the model was generating Chinese characters even when it was prompted with an English prompt. I think that's because you're using a not very good model. My guess is you're using one of the smaller open source models. And when p equals 0, when p equals 1, remember that when p equals 1, you're sampling from the full distribution predicted from the model. And so there's this long tail of not very good things that you can choose that each has a low probability, but cumulatively there's a pretty high probability of choosing one of them. And what happened when your randomness was set too high is you ended up just happening to choose random Chinese characters. So that is what I imagine is going on there. Yeah, so the tutorials are different in the sense that people are asking different questions. So the emphasis ends up being different depending on what people ask me questions about during the tutorial, but the presentation is the same. The collab is the same. So if you attended one, you can attend another, but it'll be basically the same material. Okay, so I just did something interesting, which might be cool to talk about, is I had a bug. I made a label map here for the classification example, where I set 0 to be good and 1 to be bad, which is wrong. It should have been flipped because 1 is positive sentiment and 0 is negative sentiment. So this meant that every one of my examples in my few shot prompts was misclassified. But when I ran this for GPT-3, I got an accuracy on my validation set of 6%, which really means that because my mapping was flipped, but GPT-3 got 94% accuracy on doing this task correctly, even though all of the examples I gave it in my few shot prompt, every single one of them was labeled incorrectly. Because what your few shot prompt is really actually teaching the model is it's teaching the model the structure of the task you want it to do. Because it actually didn't really matter that all 6 of my examples in my few shot prompt, all 4 of my examples in my few shot prompts had the wrong labels, because that's not what I was helping GPT-3 to figure out, because it already kind of knows positive and negative sentiment. I was just helping it figure out the structure of what I expected it to generate. So I got 94% from the fact that it says accuracy of your prompt on the 50 test examples is 6%, which really is 94% because of this bug where I flipped good and bad. Because I should have put good on 1 and bad on 0, and I made a typo, which means that if you look at my few shot prompt is just incorrect. Like this review says I had a bad experience here, and I incorrectly in my few shot prompt said good. but GPT-3 still figured out how to do the task correctly, even though the examples in my few shot prompts were annotated incorrectly. So how does GPT know what is positive or negative? I think that it knows it because it knows sort of what the words positive and negative and bad and good, like embeddings for those concepts are stored somewhere in the neural network, and the neural network's billions of weights. And so it already has an association of the words bad and good. And so even though I flipped the meaning of the words bad and good in my few shot prompt, this didn't override its internal knowledge of what these words mean. That's stored in the embeddings for these words and then in the neural network itself. All right, I actually have to head out, but I really appreciate all of you joining, and feel free to keep using the chat, asking questions on the chat. It was really good to talk to you all. Yeah, feel free to participate in any of the other events that are happening over the course of the summer. There'll be one more tutorial in July.